It's a great pleasure to introduce Kang-Kuen as our speaker for today. Kang-Kuen is a professor of chemistry and chemical biology at Harvard. She did her undergraduate work at UC Santa Barbara and her PhD at the University of Colorado at Boulder, where she was supervised by Debbie Jim and Jun Yi and did really groundbreaking work generating the first ultra-cold gas for polar molecules, for which she received the Desmont Thesis Prize. She subsequently did postdoctoral work at Caltech in the group of Jeff Kimball. And since arriving at Harvard in 2013, she's developed a really fascinating research program where she's done things like assembling molecules from the bottom up and really controlling their common states. And we'll be hearing more about that work today. I'll just say that this work has been recognized with more prizes and awards than I care to list to you. But just to give a few examples, she's a recipient of the Packard Fellowship, the II Rabi Prize in AMO Physics, and recently the Breakthrough Foundation's New Horizons in Physics Prize. So we're really happy that she's able to join us today to tell us about her latest.
Okay, yeah, it's a great pleasure to visit and thanks organizers for the invitation, and it's just really great to have this energy of the audience and students and stuff. I arrived late last night and so I started the lab tour kind of late today, but the first lab I saw was more Catfish lab, which was very, very interesting, and in fact it is somewhat related to how I got into atomic physics. I was, prior to when I was in UC Santa Barbara, there was no atomic physics at the time, and I wanted to do some modern type of experiment looking at gravity, because I was able to do a research with torsion pendulums, and I was very interested in that. And Mark's group was very, certainly top of my choice at the time. But then once I got into looking at adding the planetary, then I started to see lots of really interesting things happening in atomic physics. So in the end, I decided to go elsewhere. But that was actually, I think it was the last time I visited Stanford, which was way too long ago. And I'm very happy to actually see, all the results coming out and then be able to come back to physics. Okay, so today I wanted to tell you kind of maybe 1.5 story on the different sort of aspect of things that's happening in my lab or in the collaboration. But let me just get into it. So what I'm going to tell you, sort of the main story is showcased in this slide, where where we can build, as Monica had alluded to, single molecules from individual atoms from the bottom up. We can arrange these single atoms in any desirable way or a very flexible way. For example, I wrote down here the Chinese characters of ultra-cold molecules. And the reason you probably can't recognize is because it's probably Latin. So it's certainly an improvement, an area for improvement. So let me just say, molecules, of course, are ubiquitous, and everybody think about, every different discipline think about molecules differently. And here I wanted to sort of more focus on the quantum degrees of freedom. This is the quantum seminar anyway. We're thinking about molecules in terms of this quantum degrees of freedom. And these quantum degrees of freedom, and there are many, could allow us to really identify molecules in various contexts. So that's actually being utilized for bioimaging and for chemistry in general. For example, with the vibration transition, one can get molecular specificity information, and this is a slice of an image of a slice of mouse brain, where on the left hand side just a normal microscopy, optical microscopy. On the right hand side is coupled with these Raman imaging. You can see like which part is actually problematic. Nuclear spin is another decrease of freedom, and that's of course widely used for nuclear magnetic imaging, and this is show where water is in the Kang-Kuen. Now, in the physics domain, we often utilizing transition as standard as one of the things that physicists like to do. For example, the very first atomic clock was actually based on molecular vibration ammonium molecules. And the reason it was based on molecule was because, well, at least first sort of proof of principle was because molecule has all these degrees of freedom, which is very easy to access. You can get a bottle of ammonia gas, and you can access, and these particular degrees of freedom is in the microwave region for gigabits. So over here it says the first clock was so accurate that it will use only 1 second in 300 years, and atomic clock came a long way. So now we don't, the best clock, we won't lose the second over the edge of the universe. And some of that technology has really revolutionized our field. So what's the ticking of the clock? Let's look at this plot from basically a superposition of what we know S&P orbitals, and we can look at the electronic density as a function of time for this superposition, and that's the ticking of the clock. And this sort of generic two-level system is everywhere that you'll see a lot. When you look at two-level system, you can think about this picture of the clock, generic in many different physical systems. Of course, like the real clock is ticking much faster than what's ticking over here. Okay, so laser cooling was one of the technique that was invented to try to get better precision clocks. We don't want the clock to be running slow or fast because of the motion, so we're going to put there. So that was one of the sort of the major techniques. But nowadays we're kind of again bringing those back to molecules because molecules are more complex. It's easy to access them, but it's hard to control. But the technology has become more and more mature that we can cool and track. We can allow hold on to molecule for a long time, allow them to interact, to probe them, and to then build them, use them as building blocks, complex building blocks to even more complex systems. So in my field of ultra-cold molecules, people pursue a wide variety of different scientific directions, which I sort of categorize down here according to sort of the number of body involved in the physics. So for search for new physics, often we use single body physics, and for chemistry, where it involves breaking chemical bonds and forming new bonds, we need to two or few bodies. And then in the middle, where we often face solid phases and quantum simulation, quantum information, where one require entanglement, starting with either two particle or many, or two, and then build out long range correlation. Okay, so in my lab, we are focusing on these three scientific directions. But before I get into some of the results, I just want to broaden up to say using sort of 2 or 3 slides to give a little bit more, still broader perspective. Since I think ultra-cold molecule is not being pursued as actively here, so let me just get into some of these specific applications. So molecules, in terms of search for fundamental physics, they can be used for high, sort of nature's high electric field laboratory, and by utilizing, basically selecting, exactly the criteria you want in terms of sensitivity to new physics, in terms of, how easy to polarize the molecules, and and the molecular symmetry that one can choose to cancel systematic already current generation of electron-electric dipole moment search have been able to carry out in the last 10 years. Started really 20 years ago, but really the result came out in the last 10 years, being pushing this frontier for at least 2 orders of magnitude beyond what's possible with atom, pleasure with atom. And in the future, the field wants to use laser cooling. At least none of these are using laser cooling yet. Laser cooling of molecules or molecular ions, or assembling of exotic species to utilizing sort of the new technology that we got for molecules for another factor of 10 or 1,000 or so for these kind of measurements. So it's very impressive. One can also imagine using molecule, these 2 atoms in a molecule as a test mess to test gravity at very small scale. So this is a plot from to attempt to say what the sensitivity might be if one utilizing these Strontian dynamos. Of course, one has to calculate, what is the atomic molecular structure. One has to know the physical fact to be able to go beyond to know what is sort of the new thing that comes from gravity. And of course, in terms of precision spectroscopy, one can hold on to, say, molecular ions for a long time, and simple molecular ions. Again, comparison to theory to figure out all the terms that we push to understanding of all the exact terms that we know, and then see whether these things whether theory and experiment match. Okay, and in the chemistry domain, fundamental chemistry with molecule, a lot of these are concerning collision, concerning reactions, or concerning sort of synthesis of molecular species. For example, in this work over here, where people are able to merge 2 molecular or atomic beings so that they're co-propagating, and you can do the collision energy between them, and study collision of cross sections. And this can be calculated in principle. Actually, this is the domain of quantum chemistry calculation. And the standard, sort of the gold standard quantum chemistry calculation is this thing with abbreviation called CCSD T. But it turns out that's not including enough correlations. So the experiment is now precise enough to be able to distinguish, okay, we need to include the next order of correlation, CCSQ, to be able to match well to the experiment. So it's really sort of pushing the precision that we need from these quantum chemistry. One can also synthesize for the exotic species, and this is actually a work from Eric Cousins' group, but also already a number of years back. And now they're actually utilizing these kind of molecules, basically making molecule and then sticking in these kind of metal sensors for optical cycle and for imaging, for lots of sort of interesting new ideas. One can also attach chemical functional groups and stuff like that to do more sort of quantum science kind of things that one might be interested in. Final example here is the direct detection of reaction intermediate, and that's the work in my group. So let me just say a few more words on that. This work done by a group of students, opposed to many PhD theses of Yale and okay, so when you think about chemical reaction at very cold temperature, we're talking about sub-microkelvin, you usually feel like the chemical reaction should stop. But it turns out for these kind of chemical reaction, these molecules of bialkali that made up from bialkali, these energy landscapes are downfill in this specific case, and it has a very deep well in the middle. So the chemical reaction proceeds through reactants and chemical reaction complex, and then eventually finds its way out to the reaction product. So it's a downhill process, and nothing really stops it from happening. As sort of more, there's no barrier in that sense to stop it. So chemical reaction can proceed, and we built an apparatus not only able to make these reactants, but also be able to probe these with ionization. So we were able to actually see directly after sort of 10 years after we first made these molecules, and we see the disappearance. But what was really interesting that these complexes turns out to live for a very exceedingly long time, much longer than we typically would think of the chemical reaction complex, which will be a transient event. For that, it turns out it can interact with the light that we use to track the molecules. So then to excite them into photoexcited to different states. So essentially, we can steer that we can claim that we can steer the reaction by a very strange stage, which is the complex, which usually is strange. Okay, so but we can also turn off the light. That's actually easy to do, and allow chemical reactions to proceed and start to get information about the quantum state outcome of the chemical reactions. It turns out, although we have these chemical reaction complexes that scramble kind of all degrees of freedom, it doesn't really scramble the nucleus spin degrees of freedom. It's still a good spectator. It still doesn't really couple, despite that it spends sort of millions of vibration rotation cycles during this time. And this way, this allows us to control the outcome of these nucleus spin state in a way by preparing different kinds of superposition of the nucleus spin state of the molecule, and then have them paired up differently as the outcome. So by controlling sort of the reactants to control the outcome. So this is something that was interesting that we did. In the future, we are interested in to see whether this could be a mechanism to actually generate belt pairs of molecules through chemical reaction. We don't know. We're still figuring out what's intel, but it's a possibility because of this pairing mechanism. Okay, so to really sort of put quantum description to chemical reaction, the way one think about these problems is to calculate potential energy surface, which is a quantum mechanical calculation of placing the atoms in different positions and calculate the underlying energy, stitch everything together to make a potential energy surface. And on top of that, we can put in our molecules to allow scattering, and ultimately we want to see what happened to it in terms of what quantum state outcomes. What's the what are the possible quantum state outcome, and what is the probability? In principle, there may be a superposition of all of them until we make the projection measurements. Okay, so for that we were able to measure actually 57 different channels, like all the channels that exist in this in this reactions, and by doing a coincident detection. So simultaneously detect the quantum state of the outcome for the potassium dimer being one, and the rubidium dimer being the other one. And we can make a map like this and compare to theory. And the theory is only actually a very crude one because exact quantum calculation is too hard. The theory is statistical, where we say all the outcomes are equally, all the sub-quantum states, all the microstates are equally likely to be populated. And then we can compare our measurements to that. And we found, because we have 57 channels of measurements, we found 7 of them, here is one example, are deviating statistically significantly. We don't really know why, because we don't have a quantum calculation. So this is an area where we're more advanced in theory. And the theory has to catch up now. And that may require significantly more computational power. Okay, so this is what I wanted to say about some ultra-cold chemistry work that we've been doing, and we continue to explore these type of reactions, actually more in the domain of atom molecule where things could be simpler, but it turns out we found high orders of magnitude discrepancy between what one is expecting in terms of time scale versus what we measure. So there's still a lot of mystery when we get into the detail. Okay, so I want to now sort of get to the main part of my talk, where we pursue these individual molecules for the directions of quantum simulations and computations. Let me just again, broaden up the discussion first to say that when we think about, sort of these kind of versatile quantum systems for simulation and computation, we want to create quantum physical systems that are fully controllable, scalable, and capable of internal interaction. And of course, there are many different examples, physical realization that can realize to some extent of all of these. But I would say a big challenge certainly is still to have very high fidelity entanglement in a scalable way. And of course, there's I think lots of good progress in the last 5 years. Our approach is to utilizing molecular degrees of freedom, molecular resources to add to the list here. And these degrees of freedom I had already introduced, they're all in different sort of energy scales, then they're all in principal coherence. And we can have molecule entangle in principle through their intrinsic interaction, which is utilizing the dipole-dipole interaction. So we want the molecule to be polar, meaning that they have these charges distributions, plus and minus. A homonuclear molecule will be nonpolar. But of course, what we have been actually doing in the last 10, 20 years actually is to really to get to sort of the quantum control of the molecule, cooling, trapping, and quantum state control. So let me just make a little bit more concrete example of how we would plan on utilizing the different degrees of freedom for molecule release application. For example, for qubits. These complex but intrinsically coherent qubits, we want to tailor to the multiple requirements for high fidelity entanglement, for example. So one can imagine utilizing say spin degrees of freedom for information storage, the rotation degrees of freedom, which is the degrees of freedom allow us to have dipole interaction for entanglement for the dipole exchange, and then going between the different degrees of freedom through these intrinsic molecular couplings. So molecule has this internal coupling. So the problem will become more evaporation. So all of these will be mediated basically in the absence of any applied field. Okay, so just to give some example of what kind of coherence time one can achieve with molecule, these are just a bit of a literature summary from our field. Nuclear spin degrees of freedom in this work from Simon Cornish group, they show a coherence time of greater than 5 seconds, and in fact, they couldn't measure a decay. The decay is due to the molecule loss, so they couldn't really see a fringe decay, but they put a confidence band. Okay, so that's one degree of freedom that we know can be very coherent. Another degree of freedom which we want to use for entanglement is these rotation degrees of freedom. So for calcium fluoride, this is work in John Willow's group, where we were able to show that one can also get very high coherence through the choice of states and individual molecules side by side. Well, actually, sorry, in this case, it's just a single molecule and then put it in superposition of 0 and 1. So on the order of a half a second is what we can achieve. Now, these systems that we're working on are molecules in optical tweezer arrays, very much motivated, and actually more or less sort of starting at the same time as these configurable optical tweezer array of atoms, but molecules progressing at a slightly slower speed, but still moving very rapidly. In these configurable optical tweezer work, this is a lot of the sort of hot topic in our field in the last 5 years or so. We can have these single atoms arranged into interesting geometry, and allow them to interact with either Rieber interaction or collisions to entangle them or to have control interaction. And in our case, we're interested in molecules, so we pursue 2 different approaches. One is do laser cooling of molecule and directly tracking the molecule into optical tweezers. So this is working John Bohr's lab, and then I'm also collaborating on that. And in my group, we work on assembling molecules from single atoms. Let me just say that the molecule choice that we have is sodium and cesium because it has a very large dipole moment, and that's ultimately sort of the metric of how much of interaction I will be able to get and control. And we start with an acoustic optical deflector generated with an array of, for example, here, an array of 10 sodium and an array of. Okay, so the assembling step in one slide explanation is that we trap and cool individual atoms. We merge them into a sand trap, and then we make molecule out of it and eventually put them into the right internal state where there we will have a large dipole moment. This trapping of single atom is actually non-trivial, although it's being already pioneered since the 2000s. But if you really think about it, it's a very simple technique, and I'll explain in a bit. But it's actually quite non-trivial if you try to apply it to other systems. So the technique is the following, where one can focus light into tightly focused, through microscope objective into tightly focused beams inside a vacuum chamber and overlap it with an ensemble of laser cooled atoms, for example, and then grab individual atoms. And actually, this process is stochastic. And in our case, we use two different colors to control two different atomic species. And because of the stochastic nature of this process, sometimes we get both sodium and cesium side by side. Sometimes only one species is loaded, and sometimes none of the species is loaded. So in all these cases are useful because we can distinguish a two-body process from a single-body process. Of course, if we didn't load anything, that's okay, so, but what we can do, if we want to assemble a molecule from two atoms, we want to have a better starting point, exactly two atoms of each species as opposed to one of them only. We can do this, use this technique of rearrangement, which was demonstrated first by these people down here, where one can image the single atoms that loaded into optical tweezer, in an array, and find out which ones are not loaded, and then eliminate them, and then compact up the tweezer. And this can be applied in both one dimension or two dimension, or perhaps also three dimension. So as an example, our cesium loading probability for individual size on the order of 60%, and if we can perform this rearrangement, we can eliminate the holes and we compact from array of 16 tweezer to say 8, then the probability of loading then after this rearrangement are much higher than we have initially. Okay, so that's a new starting point where we can rearrange them into individual as close to unit filling as a starting point. The next thing is we cool them and then we merge them. We physically bringing the tweezer from different location onto this is trap depth versus position onto the same position, and we remove one of the color so that both atoms are trapped in the same location. And this process has to be adiabatic in such a way that the atoms actually prepared have been cooled to the motional ground state, and then so we continue that process. When we merge them, they're still in the motional ground state. Okay, so now we're ready to make a molecule, but that turns out actually it's quite challenging on paper, and it's technically also very challenging, but we have a solution. So let me just tell you about the challenge first. In the best case scenario where we prepare two atoms in the motional ground state, the wave function spread of the individual atom is still sort of the 0-point motion, which is on the order of 50 nanometer in the sort of the weak direction. Okay, comparing two atoms that you'll find in a molecule, the two nuclei are really pinged well and their separation is 0.2 nanometers. So the probability of finding two atoms at a distance that you could make a molecule is very, very low, of course, because this is like you couldn't really think where the atom is, and now you have two using dimension. So this wave function overlap is 10 to the minus 8. So to go from atom pair to molecule, that wave function overlap is very low and makes this process very challenging. Now, in addition, to form a molecule, we have a binding energy. We had to release binding energy. We had to release thousands of kelvins worth of energy in the process. So all the hard work of preparing atom in motion and ground state would be wasted if the molecule in the end get heated up by this energy. So the solution actually was part of. It's now being demonstrated in many group early work for my PhD work in a bulk gas of starting with bulk gas and atoms. And then the approach is the following, where one can bind the atoms first into a weakly bound molecule, do a scattering resonance, which I won't get into too much detail. Feshbach resonance, functional Feshbach resonance, to make Feshbach molecule. And what this step does is to prepare the molecule in a single quantum state. Okay, so this is the process. You electromagnetic field, prepare them in a weakly bound state, but not yet in the raw vibrational ground state, where they will be appreciable dipole moment. And that's where we would use the two-photon process to transfer the molecule down to the desirable state. And in this process, the stimulated photon take away that 6,000 Kelvin, thousands Kelvin worth of binding energy, so the resulting molecules are actually just as and because we do these state preparation, constant state mapping from one state to the other, this can actually be quite efficient, 30–40%. Of course, we want 100%, but okay, but compared to 10 to the minus 8, this is a significant number. So this is the approach that we make molecule, and like I say, it's been done in many different species in bulk gas, atomic or optical lattice, and our sort of contribution is to start with exactly 2 atoms to implement such a technique. Okay, so what I wanted to say, a punchline here is that we mapped all the control of the atoms onto the molecule. So the molecule resulting is let me maybe just go through it very quickly. When we think about making molecule from 2 atoms, we can think of the atoms as individual, or there is pair in terms of their freedom. So atom pair can have these couple motional degrees of freedom, or their relative degrees of freedom. And for molecule, you still have that motional degrees of freedom when they move together, or these relative degrees of freedom are rotations and vibrations. So going from atom pair to molecules through these magneto association process, it actually maps from one quantum state to another, a single quantum state. So the end result is that molecule in a single internal state and predominantly in the motional ground state are prepared to do this process. Okay, so now individual molecules are fully controlled, and we want to start to manipulate their interaction by manipulating their rotation degrees of freedom. And this is the dipole interaction that we want to leverage. The dipole-dipole interaction is usually written in the following way, and we can actually map these say even classical dipole-dipole interaction onto the quantum version by treating these as operators. But the important thing is that, without elaborating into any detail, is that in the absence of the laboratory, so in the absence of a polarizing electron field, we can basically think of these dipole-dipole interactions in the language of spin. And the spin, for example, only the plus minus and minus, the exponent. where these interaction strengths in front are depends on the geometry of the particular molecule state. You choose their geometry in terms of distance and their relative orientation. Okay, so the dipole interaction resonantly coupled rotation state of a nearby molecules. These are the rotation state we labeled n as n to the 0, n to the 1, and they're really just these S and P states. Different from electronic in the sense they're the sense spherical harmonics, but different from a typical electronic state in terms of their energy. So these are the S and P state, these are the n to the 0, n to the 1 state that couple through these dipolar interactions. That can be leveraged. Okay, so in the molecule world, these resonant dipolar exchange interaction have been observed in a few systems. For example, the first one was in 2013, where molecules are placed in sparsely filled optical lattice. In the Giller experiment, they showed characters of this dipolar interaction. Almost 10 years later, they're now refining their control so they can prepare molecules in pancakes and prepare their state to be, for example, O in n to the 0, O in n to the 1, and O in n to the 0. And then they can see the interaction going flip between these layers. And that's the work shown here. And we are interested in pushing that even further. We have individual molecule control, so we can also imagine individual state control of the molecules that we prepare. There's a couple of different works done now, and just wanted to also mention that in Watson Black Princeton, they built a quantum gas microscope of molecules, so they don't have individual control of the molecule yet, but they can have individual detection of the molecules. So here are the character of the dipole interaction between selected pairs that they can get from these individual states. Okay, so how do we prepare molecule in included 1, 0, 1, 0, 1, 0? Well, the challenge here is that microwave radiation is on the order of 10 centimeters for 3.5 gigahertz, and these tweezer saturation is only on the order of micron. So in order to, the microwave doesn't have the size selectivity, but we could play a trick, which is actually a very important one that I'll elaborate on in the next slide, is to use Stark shift. So basically, linear polarized tweezer can lead to actually very large Stark shift, this interaction between the light and the molecule, such that we can basically shift the resonance significant amount, so that we can, by putting on different intensity, we can basically selectively address the transition from 0 to 1. So that's how we would do it. But one could also imagine, this could be problematic because now you have this really large intensity that could fluctuate, variation. We actually use a separate tweezer, which we have handy because we have that for studying initial loading to map onto this, to site selectively address the ones that we want to shift away. Okay, but nevertheless, these light could cause a big problem, and this is sort of I would say the biggest problem with these kind of systems is that these molecules are completely isolated, everything, but it's being held by light. And this light is sort of the biggest problem. They can cause all kinds of interference if not managed well. Okay, so this light shift turns out to be quite large, as I was telling you. We can shift the resonance completely. So even with a small, attempt to make them the same, they're still quite. They can still have. With just fluctuation of the intensity of the tweezer can cause problem both for single body decoherence, but also for if the two molecules side by side, the intensity are slightly different, then the resonance condition will not be met, and then these resonance bipolar exchange doesn't occur. So that's the biggest problem. And how big is it? We can characterize it. So it turns out for linear track, we have all the different, in the unequal to 1, we had the different sort of p orbital oriented into different directions. We can measure these shifts, and these shifts are on the order of hundreds of kilohertz per megahertz track that we apply. So it's very large. To be compared to sort of kilohertz dipole interaction that we ultimately want to get. So what we want is a slope that's 0, so that we can eliminate these things. But let's look at these differential relationships of molecules. So molecule, these diaphragm molecule looks like this. If we polarize them, their polarizability is different if we polarize them this way versus that way. Right? It's very natural to see that if you polarize along the axis of the molecule, you have a polarizability that we call alpha parallel. And then if we polarize it, quantization axis is different, then that's alpha perpendicular. And the alpha parallel is much larger than alpha perpendicular just because, which axis lined up with the molecule. Now, for these, okay, so let me just say that for n equal to 0, it's really a linear combination of all these 3 axes. So the polarizability is just the sum of all these 3 different axes. For n equal to 1, if you have some quantization axis, then these eigenstates are all pointing in different directions. They will have, if it's for this one, it will have alpha parallel, but if it's, the light is the quantization axis is some other direction, then it's the polarizability is alpha. Okay, so this is for n equal to 1. So in order to make then the descent for 0 differential light shift, to eliminate differential light shift, one solution is just to put a quantization axis at a particular angle such that you have a sum of the different orientations, and that was shown and it was demonstrated in a wide variety of different modes. But it turns out this one doesn't really quite work for us because the tweezer is actually quite intense, and also the coupling is slightly different in our molecule, and therefore we're in more of a stronger light limit where the light polarization align the eigenstate. So if we turn that, so these are the 3 eigenstates pointing in 2 different directions. If we turn the polarization directions, then the molecule just rotate with it, and therefore we don't get this combination of, the magic combination. Okay, so we need to have a new way, which is we use magic ellipticity, which is, again, we have, these 3 different axes with a particular ellipticity. Depends on orientation. It turns out one of them with the right ellipticity, you can have exactly this combination. Okay, so if we were to calculate, these are the linear track, these are the states, and then if we're matching ellipticity, we have a state that looks like this, a state like looks like that, but one of them is actually have a slope of 0, and that's what we're hoping to do. Now, experimentally, we had to implement these ellipticity control actually in the middle of the sequence because we want to have different polarization for different purpose during the molecule making process. For state preparation of the atom, we need linear polarization for pumping and cooling. But then once we make a molecule, we want to rotate in the middle of the sequence to this ellipticity angle, so the quarter wave play change angle such that we can have this magic. So we now place our rotating stage. This is the one that we have been using, although we just recently upgraded it. We don't. It's a little bit slow, and then we're sometimes not sure what exactly it's doing. It's the main problem at the time that we care about. So anyway, we put it right here before the objective, and then we have a quarter wave plate that rotate in sequence on the order of sort of 50 milliseconds. Okay, so with that we can measure the 3 different states, and one of them is indeed sort of no light shift. We can measure as a function of track dash and vary these rotation angle a little bit to see how much differential light shift we get. And with these 2 track dashes, we have a 0 crossing to pinpoint the exact rotation angle that we need on the quarter wave plate to achieve this magnetic. So we've improved this slope by a factor of 2,000. So we reduced the light shift by a factor of 2,000. You see a coherence time of the system increased by a factor of 20. Not quite the 2,000, and we're still trying to figure out why, whether something else is limiting our coherence. But this is actually a really nice demonstration, and we're very excited about this because now we can finally, worry less about this intensity. We still try to do a good job with intensity servo, but previously it will be insane if we don't control that. Now, there's also polarization gradient that one will probably encounter between the different sites, just because polarization is such a hard thing to control in an experiment like this. So we can characterize that, and that's on the order of less than, correspondingly less than kilohertz for the negative. So we think this will be sufficient to see kilohertz dipole. Now, what was really interesting and we didn't realize until more recently was that as we turn our so our polarization ellipticity is now a quantization axis, and the dipole-dipole interaction is not is anisotropic, so it depends on the orientation of the quantization axis versus the position vector between the dipoles. So actually, interaction strength as a function of that angle, the angle that these axes make relative to their separation, actually varies, could be from negative to positive. And it turns out, just the orientation that we have, and starting with a particular polarization and turning ellipticity such that we have this perfect magic ellipticity is exactly at zero crossing in terms of dipole interaction. So the good thing is that we can control that, with additional half-wave plate to basically orient the ellipse in the laboratory frame. It's just like without that, right now they're exactly at this canceling zero. So that's something that will work to orient that so that we can actually see, we can turn the dipole interaction strength and different signs. So we expect sort of millisecond or kilohertz kind of interaction for a 1.7 micron molecule separation. Okay, so in the remaining 5, maybe 7 minutes, I wanted to tell you another single molecule experiment, which is in this collaboration in John Duo's lab, where the comparison of the two approaches, they are really quite complementary in terms of what it takes to get to the quantum state control and what it takes for detection. And these calcium fluoride molecules are very nice for detections because they just fluoresce. Laser cooling light on them, they just fluoresce. So you don't need to assemble them. First you don't need to assemble a molecule; they're just molecule. You have to cool it down, and second, you don't have to break them up again to the image. So all the maybe one step that I didn't mention was all the work with sodium cesium. We always assemble molecule and we break them up to see the individual atoms to know something about the molecule. Well, in the calcium fluoride case, we don't. But these molecules are not as cold. They usually are only laser cooled, and then we can purify their internal state. They're emotionally still relatively hot. And that's something that we're actually working on now to do sideband cooling of these molecules. Okay, so this is what I want to spend a few minutes talking about. And this is actually already in the second generation, even though laser cooling molecule I only realized 10 years ago. That now we're going to the second generation apparatus, and these are just pictures of the source, the glass cell, and the vacuum. These are the people who are responsible for these results. Okay, so some highlights. These laser cool molecules are now can be also very large. Some people will call calcium fluoride like the ingredient of atom, the ingredient of atom. calcium chloride is the important molecule. So all the laser cooling trick sort of work for calcium chloride. One can have a very large amount that you can see with naked eye, right here, and we transport from one chamber to the other through these tunable lenses overlapping with optical lattice by on the order of 50 centimeters. And then we land these molecules into a glass cell with the optical axis and a very large objective shown here. We can project lots of tweezers, so this is an array of 60 single molecules, an average image. Each dot here is a single molecule. Okay, so with this, we can do all the same tricks, although these molecules are still relatively hot, but actually quite surprising and quite impressively that by bringing the two molecules close together, pairs of them and copies of them, we can see dipolar interactions about the order of 1 to 2 ranges as a function of separation. So this separation, as you would expect, dipolar interaction drops off as 1 over r cubed. They scale sort of as what you would expect. It turns out things are not perfect, which will be, the scaling will be perfect if it's follow the dashed line, because that they are still relatively hot. So like it's really sort of in terms of some kind of average position and some position. More significant, the interaction is stronger than other positions. So it deviates on that, but it matches more power. I should also say that the single particle coherence time one can extend. This is required to actually see these relatively slow dipole interaction, and through these spin echo pulses or XY pulses. And one other thing I want to mention is that this work was also demonstrated with calcium fluoride in Lawrence Chuck's group. Okay, so with these dipolar interaction and then the motion actually, these coherence evolution is kind of limited by the thermal motion. So I mentioned that like these molecules are not very cold, but actually due to the emotional averaging, one could actually already see these dipolar interaction, even though without, because of these interactions are slower compared to the motion of the molecule in the drug. Okay, so now with these dipolar interaction, one can actually utilizing these interactions to entangle the molecule to generate Bell states. And I won't go into too much detail. Basically, you just need to wait the right amount of time for the interaction, and then that interaction will be and then I swap gate. Okay. So and that time is actually a quarter of a cycle of what we see in the previous page of dipole interaction. And the way to verify you have entanglement or to calculate the fidelity of Bell state generation is through these parity measurements. So basically, you can have kind of Bell states, and then you can change the phase relative between the two Bell, the up plus the phase plus down. Okay, so the raw fidelity is actually 0.3 is not so good, but this is actually limited by the state preparation and the detection. If we correct for that, it will be much higher. So that's certainly some criticism that we might have for such a system, even though this is the very first demonstration. Okay. So can we do something about the state preparation? Well, it turns out the main detection error comes from we have these rotation 0 and 1. We can just think of it as spin up and down. We can only detect spin up, and spin down looks like an empty side, an empty track. And sometimes that's actually an empty track, and sometimes it's just down. So we need to exclude these empty sides in a way that we can select. So it's due to first due to low state preparation efficiency, or the fact that we just can't simply distinguish these empty trap from down orientation. Okay, the way that we can select that is we can first image, do this parity projection measurement. First image the upstream, and then we can employ an additional pulse such that we can flip down to up and image again. And if we do that, and we find, indeed, we see down goes to up, then we know that was down, and then if it's nothing, then that was empty. So we can exclude these empty tabs using this additional pi pulse and imaging pulse, and with that, we were able to get the data, which has much better contrast, and that actually has developed fidelity reaching 0.87, which is consistent with the span-corrected fidelity. So with individual molecule detection, addressability, tunable dipole interaction demonstrated for entanglement, now molecular tweezer systems are programmable. So with that, I wanted to just quickly summarize. So it's a very exciting time. We're now able to control, prepare molecule individually. We have two different systems. They're slightly different, and for the case of sodium cesium, we had to use magic ellipticity, and we're close to getting the dipole interaction to work. So we're working on that actively. For calcium fluoride, it turns out the selection of the state, the first order, there's no differential start shift, so that the starting point is 1,000 times better in terms of not having to work on that intensity fluctuation or cancellation. And even though these molecules are still relatively hot, but that sort of motional average was effective to allow us to see the first dipole interaction with molecule in tweezer and utilize it to entangle molecules for the first time. These ultra cold molecules. So, and of course, we're, like I said, also looking for these interactions in sodium cesium, which we expect the coherence to be much longer because these molecules are already in emotional gas state. So these are sort of the wide variety of things we're pursuing for these molecules, and I just wanted to end on one note where we are also pursuing Reaper atom physics, and with geometry like this to study physics with periodic boundary conditions. Okay, so with that, I wanted to acknowledge the sodium cesium team. This is a group. This is a group photo from last year, last spring. Flowers is not like this yet, but last year it was very nice. And the sodium cesium team, the apparatus was built by Jessie, and for her thesis, she did making these array of molecules, and now we are down to 3 people. Just post that any students Gabriel and Bruce. And I also want to thank you for your
starting with questions for students.
Yeah. So when you were assembling molecules by essentially just bringing the two trapped atoms together, so I understand how you were able to detect whether or not a site was empty or full when you had individual atoms, but after you assembled the molecule, what were you doing in order to actually, were you just using a different wavelength? That was...
Yeah, so this is, that's a very good question. So it is, right now the approach is just coherently reverse the process. Mm-hmm. So
okay,
make a molecule, we think we make one, but we don't know, and then ultimately at the end of it, we break up the molecule through the same procedure and then detect them atoms.
Okay. So ultimately you're detecting the individual atoms just after you break it up. Yeah,
exactly. But we are working on a way where we can do a little bit better, because it turns out the inefficiency of converting atoms to molecules is because the atoms are not in the ground state, motional ground state. So we want to image the atoms directly, while the molecules are protected because they're really far resonance. So, and if we see sites that they're atoms, and there shouldn't be a molecule, but there's atoms, we know we didn't make molecules. So that way we can eliminate some, we can, we improve our baseline in a way. But it's not 100% because there is ultimately still the process of steroid, which could be 90%, that we won't be able to do that.
Thanks.
So I'm wondering, could you use extra atoms in nearby tweezers and do some like blockaded detection or something?
Yeah. So we actually have kind of worked out. Let's see, like maybe over here. So like actually there's sort of several different possibility, like either it's like gates or for detection. So the atoms nearby, we have selected states where these atoms, reverse states, the dipole moment is actually like 10,000 times bigger than what we have in molecules, and then so through interaction between atom and molecule, we can map that quantum state to the atom and detect on the atom. Or we can also insert it into molecules and switch on that interaction. So in principle, in that same lab, we had the Reaper team and we had the Reaper laser, so we can do it, but it's always like, anyway, so so we very much hope to do it. So we still have. Great.
Yeah, for this L state delay, so what limits the remaining 10%?
So a large part, they're both technical, but also so the technical is a different thing that has to do with working with acoustic optical reflector. But then a large part of this infidelity is due to the motion. I don't have a calculation here, but it is because, basically because over here you can see the coherent oscillation dies out very quickly. So, and that comes from the fact that these molecules are not cooled down to the Hermitian graph or to the cold temperature. So in principle, you imagine this dipole interaction that goes at 1 over R cubed, that R is changing, depends on the realization. I mean, in this case, like they're kind of averaging all in the trap, so that's why we still have some fringe, but already it's too hard to have a long view. So that's mostly we think that's mostly the technical part is turns out as we bring them closer, there is often feeding between these tweezers, and that causes some additional feeding.
So then how much can be improved by better cooling atoms? Like, is it kind of fundamental limit in the end?
I think it really like, I can do like cherry picking in the sense of, these molecules are less sensitive to light shift at the sacrifice of slightly lower dipole moment because once we choose that state. So then these time scales are relatively slow, as you can see. This over here is maybe 2 milliseconds. The sodium cesium molecule we're working on, we haven't seen the dipole interaction yet. That has a larger dipole moment, and with the canceling of the light shift, we expect 1 millisecond, and it's in the motion of gas. So we have a high hope that that will be significantly higher, but detection is harder. So so if I can have like better, both of the both world, then that would be the best. But it's hard to get it in one system. So I mean, in my original sort of proposal using dipole dipole exchange, we project 99.99. So like we discuss what are the limiting factors, and ultimately the limiting factors are actually leakage error. It's because like in sodium cesium, the hyperfine states are not that far away, so then one has to kind of slow things down a little bit so that you don't go to the wrong state. But like in terms of coherence, in terms of motion, and all these can be managed. So that's So that's my long answer.
Great. Good questions?
I have one more. Is there one that?
Are there any or John? No? Okay, all right, we'll let you go.
My questions are like chaos, they will fill face. You made a strong case for molecules broadly, and I kind of feel like the hardest argument to make for molecules is for quantum computing. Right? What's your take on that compared to, say, Rydberg's? Is there a reason to go the molecule route as compared to the Rydberg route?
Well, I mean, I think, yeah, I mean, I would say yes, and I think Rydberg, I mean, different system has different limitation, and I think the Rydberg, I'm not sure, like, is the Rydberg, like, the ceiling is ultimately kind of the Rydberg lifetime. Okay, one has way to get around this, is going to, I mean, that's a different development, yeah, right? So, like, typically people, put a number of 99.9, and that's due to the lifetime. So in molecule, in principle, we don't have that problem. So if that raw fidelity is what we're looking for, the one, at some point we'll probably get there, but of course it'll take a while. But in terms of absolute time scale of gates and stuff, these things also matter. So I would say these leakage error is a problem for sodium cesium, but it should not be a problem for calcium chloride type of molecule because they actually have spin error hyperplane more well resolved. So I mean, I think the case for molecule is that you have so many choices, and you might be able to, just like precision measurement experiment, might find the right molecule for the purpose. But we don't quite have that yet. We don't know what's
Can I follow up on the question about timescales? I'm wondering, in terms of sort of pushing things faster, would it make sense at some point to actually load into a lab sort of accordion level system?
Yeah. I mean, it's certainly, tweezer certainly has some limit in terms of how well you can resolve the two swaps. And it's a steep function of systems. So so we're working on some second generation apparatus where we want to combine tweezers, but then you lose a little bit of the individual control. I mean, you could just kind of add it off the file. But that's not exactly easy, right? So, yeah, but certainly that's also a direction.
Great. I think we should probably let people go. So thanks again for the call.